that various problems are undecidable, and we will do a string of these, a whole bunch of these, in this chapter. So if A is reducible to B, problem A is reducible to problem B, and if A is undecidable, then we can conclude that B is undecidable. But he doesn't actually prove that. Alright. Or does he? That's the thing about Sipser. Alright. So now here, again, I've put two vertical bars. Not so much a definition, but just important. Okay. So the method we'll use throughout this chapter is how to prove that a problem B is undecidable is to show that some other problem A that's already known to be undecidable. In fact, this is just a rewording of what I've just been saying in the previous square. Okay, reduces to it. So let me put it this way. It's just a rewording. So you reduce problem A to problem B. Okay, and problem A you know is undecidable. Therefore, problem B is undecidable. So, if you want to prove that problem B is undecidable, then you find some undecidable problem, A, and have it be reduced to B. Hope you follow that. Okay, here is sort of, this is me saying this. This is Sipser, but this is me. So you know of some problem that's undecidable. Call it A. It's undecidable. Okay. Now, if you can manage to reduce that A to some other problem B, well, then you know that this B is undecidable. So, if what you're trying to show is, if you're trying to prove that B is undecidable, well, your strategy then is take some undecidable problem. Now, the only one we know of so far is A suffix Tm. Okay, so that's what our A will be. Problem A will be initially, until we can build up a supply of other undecidable problems, languages. Okay, so we have some problem B, and if we're trying to prove that it's undecidable, how do you do that? Well, it boils down to just taking some problem A that you know already previously is undecidable, and have that problem A reduced to B. Because if you can do that, if you can reduce A to B, and you know that A is undecidable, well, therefore you prove that B is undecidable. Okay? And that technique, that strategy, we will use a lot this chapter. So that's why I've sort of put double bars here, sort of important. Okay? Well, I think I've said it a couple of times already, so I won't go over it again. Because you can always rewind, right? This is not a classroom lecture where profs say the same thing over and over for reinforcement. You can give yourself your own reinforcement. You just rewind. This is a video lecture, not a classroom lecture. It's not real time. Okay, so all this sort of preliminary. Now we get into our first section in the chapter. So chapter 5, section 1. And we're now going to talk about a certain category, a certain family or class of undecidable problems, and they're from language theory. Different kinds of languages. Languages in the sense of a set of strings. That kind of language. Okay. So let's talk about a language that we'll call HALT, TN. And what is that? It's we need to define it. So here's the definition. 3 bars definition. So here's the definition of this language. Just set of strings. These are the strings. And ordered pairs. Each element of the string. Sorry, each string element of the language is an ordered pair, where M is a Turing machine and W is a string that goes into this Turing machine M, and the property of this member of the set, for it to be a member of the set, the condition is, property is that this machine M halts, okay, on W. In other words, it accepts or rejects. Okay, that's a little different from what we've done before. Before we had like M accepts W or something like that. But here, now, this is the language. That's the set of these elements, and M halts on the input W. So this is a set of all possible M's and all possible W's. So you can translate this language problem into a computational type problem. I've been doing that quite a lot last chapter or so. In other words, given some random Turing machine, some random tape W, will that machine halt? Yes or no? That's the halting problem, Turing. Translating it back from a language into a computational problem. Okay, so here we have a language, new language. Haven't seen it before. Well, sort of. Right. Now we're going to use reducibility. We're going to use this idea here. We will now. For the moment, we only have one example that we know of an undecidable language, and that's A suffix Tn. Okay, that's the only one we have. So if we're going to use reducibility, we're going to have to use that language. So our A here that we have prior knowledge of, and we know about it previously, we're going to reduce ATM to B, and this will be our B. Right? We're trying to prove that this language, this problem B, is undecidable. That's what we're trying to prove, and we'll use this strategy to do that. So in other words, we will take the ATM problem and reduce it to the halt problem. Okay, and if we can do that, we then know that this must be undecidable. Why is that? Because of this. If we can reduce ATM to B, in other words, halt TM. So if we can reduce ATM to halt TM, we therefore know that halt TM is undecidable. Right? Because what we did in the previous square. So we will do this quite a few times in coming sessions. Right? Still got the flu. Its symptoms not as severe. Each day there's some progress, thank God. But I'll stop here and just move on to the next session. Okay.